Hi guys, this is a short training on using Verilog for FPGA based design. So we'll be covering in different blocks. In the first block, I'll cover logic design. Uh, Basically, it won't be a full-fledged logic design, but it will be a review of what basic building blocks we use in the logic design process. We'll cover a couple of design examples to refresh your ways of designing stuff, and then we'll start Verilog. In Verilog, we'll cover basic building blocks, modules, gates, mux, demux, registers, and how data values are used, and we'll do a coding example. This will be followed by Verilog for simulation, which is kind of different from Verilog for synthesis. That's the first part. And in that part we'll be writing test bench, and we'll be running simulations. Then we'll try to synthesize the design that we have made. When we are certain that this is working fine, then we'll actually port it on an FPGA and test it. And then there will be another section on state machines. So this is the first presentation, so that will be covering the first block, that is logic design review. Okay, so normally we use this term register transfer level, or RTL, in multiple meanings. One meaning is that when we say that we have an RTL level diagram of a design. Another thing is that when we say that RTL is ready, then normally what we mean is that we have already written the Verilog code or tested it. So Verilog or VHDL are two popular languages. Will only be covering Verilog in this section. So what are the basic building blocks in logic design? Uh, Basically, when we say we have a RTL level diagram available, we mean a diagram that comprises of roughly these components. It can use gates, multiplexers, demultiplexers, registers or memories, and then adders, subtractors or multipliers, and we can have state machines or any combination of above. Uh, so what are gates? These are the common symbols used for the gates. If you remember correctly, this first one is called AND gate. AND gate outputs 1 if all of the inputs are 1. If any of the input is 0, output will be 0. This is called OR gate. OR gate outputs 1 if any of the input is 1. So this is that means if any one input is 1 and rest of the inputs are 0, it will output 1. If all of them are 1, it will still output 1. It will only output 0 if all of the inputs are 0. So similarly, the AND gate, if in AND gate, if any of the input is 0, output will be 0. This is called XOR gate. This is very similar to OR gate, but normally XOR gate has two inputs, and it outputs 1 if only one of them is 1. So if one is 1 and the other is 0, or other is 1 or this is 0, then output will be 1. But unlike OR gate, if both inputs are 1, XOR gate will not output 1. It only outputs 1 if exclusively only one input is 1. This is symbol for NOT gate. Sometimes we use this symbol. Sometimes we only insert this circle that we normally call a bubble. We insert a bubble, and by that we mean there is a NOT operation going on. There can be a bubble in front of AND or XOR. In that case, we call it NAND, NOR, or XNOR. That means that the output is passing through a NOT gate. Okay, next thing that we use is a register. A register can store bits. Normally it has n bit input and it has n bit output, and it can store that input for one clock cycle. So clock is a generally a tick that is going on. It's basically uh, oscillating signal that is 1 and 0, 1 and 0, 1 and 0. So we normally work on rising edge of a clock or a falling edge of a clock. By rising edge, we mean that when the transition is from 0 to 1, or by falling edge, what we mean that if the transition is from 1 to 0, most of the circuits work on rising edge of the clock, but at times we use falling of the edge of the clock as well. So let me explain with a diagram. Normally, there is also a reset signal which sets its initial value to a known state. Normally, it's 0. So what we do is that clock is a signal that is going on 101010. So this is called a timing diagram. From left to right, time is increasing. So clock is 1 for a while, then it is 0, then it is 1, then it will be 0, then it is 1. So let's say we have at the input value 3. So by this these two lines and 3, we mean that at these n bits, the binary value of 3 is input. So for example, if it is 7 down to 0, that is 8 bits. So then the value will be 0000011. So if there is 3 at the input, and if this is working on the rising edge of a clock, then when this rising edge of a clock comes, the output will be 3. So before that, we don't know the output because we don't know what was the input at the previous value. So we are showing it by x. By x, we generally mean we don't care what was the value before that. We have started looking at the values from this rising edge of a clock. So if in the next cycle I input a value of 4, then at that rising edge of a clock, since input is 4, the output will be 4. Similarly, in the next cycle, if the input is 5, so at this rising edge of clock, input is 5. So in the subsequent cycle, output will be 5. So this is the common working of a register, that it stores the value at input for the next clock cycle. If the value at input was 3, it will be stored. If it was 4, then 4 will be stored for one complete cycle. In between, if the value changes, it doesn't matter. But before a small amount of time that we can call setup time, before that clock edge, and the value has to be stable, and that value will be stored in the register. We often call it that value is latched in that register. Okay. Uh, Similarly, very often we use another signal called enable with the register. So what enable does is that that if this register will work only when this enable signal is on. For example, if we say that at this clock edge we have this enable signal to be 1, so that means that before this clock edge, in the rest of clock edges, we didn't have this enable signal 1. So that means that the value won't be stored in the register. So register will retain its old value, whatever it was. So only at the clock edge, when enable is 1, the value will be stored. So this gives this register capability to store values indefinitely. So for example, if we stored a value here, it might be a result of any computation, and we might need it maybe 3-4 seconds later. So that means that could potentially mean millions or billions of clock cycles afterwards. Because this clock is generally very fast. On FPGAs, we are generally talking about 100 mega cycles per second, and on A6 it can go to in giga cycles per second. So a few seconds is a large amount of time from digital design perspective. So if we need this value after a couple of seconds, then we need to store it for a while. So if we don't assert enable for that while, this file will be stored in this register. Okay, so next component is a multiplexer. A multiplexer works this way, that we have multiple inputs and a select line. For example, if there are 4 inputs, then this select line will be 2 bits. So what it does is it selects the input to be forwarded at the output. For example, if the input is 0, this will be connected to output. If input is 1, this will be connected to the output. So and so on. So it can be 3 inputs, 4 inputs, whatever we want. So this is working of a mux. Sometimes we call it a select line. Sometimes we also call it an address. The opposite component of mux is called a demux. Demux works this way that based on select line, if select line is 0, we connect this input to this output and connect rest of the outputs to 0. If select line is 1, we connect it to the next output. If it's 2, we connect it to next output and so on. So this is called demultiplexer or demux in short. So these are the more commonly used components. There are more to follow, but I'll do a small example here. For example, a very common component used in digital circuits is called a register file. Register file means that we have a set of registers on which we want to store some value. So for example, I have some registers. Let's assume these are 8 or 16 registers. So what we do is we have a single data out, and what we want to do is we take as an address as an input. For example, if address is 0, we want that this register should be connected to output. If it is 1, then we want this register to be connected to the output. If it's 2, we want this register to be connected, and so on. So what do you think will be the component that we should use here? Pause the video for a moment and then resume it when you come up with the answer. So if you have thought it through, then it should be a mux that should that will do the job. So if address is 0, this register will be forwarded. If address is 1, this register will be forwarded, and so on. Similarly, in a register file, we want to write on the registers as well. So what we want is that whenever at a rising edge of a clock, this write signal is asserted, then we want to write on any of the register. And what we want to write, we give it as an input. We call it data in. So if the address is 0, we want this data to be written on register number 0. If the address is 1, we want to write this data to register number 1, and so on until the rest of the registers. So pause the video and then think about it. What could be the circuit to do the job? So I'll resume it later. Okay, so if you have thought about it, then the best approach to do is to broadcast the data to all registers and to demux the write signal to all the registers as an enable signal. So what it means is that if we want to write 10 at location number 3, so I'll input 10 at all the registers, but since the write signal is used as an enable, so only enable of register number 3 will be asserted and enables of rest of the registers won't be asserted. So since the enable won't be asserted, uh, so those registers won't be written. So it doesn't matter if they get the wrong data because it won't be written anyway. So this is a common mistake. Maybe if you thought about it, if you used only one demux, at times people use demux on the data line. So this is a very common mistake that we made, and that was the whole purpose of this design example. Okay, so this register file also gives a conceptual model of a memory as well. So when we talk about memories on FPGAs, so what we mean is that we want to give an address and a write signal and a data in signal, and we want to write to that address. It's slightly different than reg file. It generally has a delay of 1 clock cycle, but it gives a good conceptual model. And normally it's not memory is not implemented as a reg file. It's generally implemented differently, but conceptually you can think of it as a small memory, and on a larger memories that we generally call block RAMs on FPGA behave similarly, only with one difference that we have 1 cycle delay in the output. Okay. In addition to multiplex, demultiplexers, we also can use adders, subtractors in our design. So generally, if we have n inputs, then the output is generally 1 bit higher than that, because if we add two maximum numbers in n bits, we'll get a number that cannot be stored in n bits. It has to be stored in n plus 1 bits. Many a times we can ignore that if we know that our output will be within range. Then in that case we can have output of n bits as well. Normally adder subtractor can be designed combined as well, so that we have a control signal that asserts. When asserted, it can subtract. If it is deasserted, we can subtract it. Additionally, we can have option to saturate output as well. So if we don't have n plus 1 bits, we only have n bits. So we can have an extra logic, some extra logic to make sure that if output is going out of the way, then we cap it to the maximum value instead of having a random number at the output. Similarly, multiplier multiplies two numbers, and normally if we multiply two n-bit numbers, the output can be of two n-bits. So again, there are options to have signed and unsigned multipliers, and again, we have option to saturate it. So these are the generally building blocks that we use. So now we do a couple of examples. We first start with a simple example, which is a simple decrementer capable of counting numbers on clock cycles. You can imagine it like a traffic signal. So on a traffic signal, we have a down counter that keeps counting down till we reach 0. So we want to make that kind of a decrementer, and then we'll cover another a little bit complex example that is a 4D FIFO. So what is a decrementer? First of all, when we want to design something, we make a black box and we write all the inputs and outputs, and then we think of it, what can be done about it, and how can we design it. So now, since you already know all the building blocks, we'll be using only those building blocks to try to make this decrementer. So what we want to do is that we want to have a value of count, and we want to have a load signal that if I assert load for a clock cycle on that rising edge of clock, I want to save the value, save an initial value in the counter. So let's say I assert load and I save the value 100 in the counter. And then I want to, whenever I want to decrement it, I want to assert the decrement signal. For example, if it's a traffic light, then I can load a value of, let's say, if it waits for 60 seconds, I can load initial value of 60. So I'll assert load and at the same time apply 60 at initial value. So that will be loaded in the counter. So we'll have output 60 at that moment. Then after every second, I can assert decrement for one cycle, and on that rising edge of clock, it will be decremented by one, so it will be 59 in the next second, and so on until it gets to 0, and that value we can see at the count. So what do you think we can be done? You can pause the video and think about it. I can give you a hint first that normally how I design these circuits, I just first put whatever thing is necessary to be without which we cannot design the circuit. So when I put it there, then I think of it that what can be added next and what can be added next, and that way I just draw it. So pause the video and think about it. Okay, so this is how I would design it. So first of all, I need something to store the values. So I definitely need a register in there. So that's the first thing. Next thing, when I think about it, I need to store this initial value in this register. So that is one thing that need to be stored in it. But it's not only this initial value. I also want to store the decremented value. The decremented value will be from the same register and it will be decremented. So this minus minus means that I want to decrement it by 1. So since there are two values that I want to store in this register, but register is only one input. So if there are multiple options and we want to select between them, we generally use a mux. So I'll add a mux here. So that will select whether I want to store the initial value or whether I want to store the decremented value. So when we add a mux, so this mux is selecting between two things. So it has a select line. So what will be the select line? So pause the video and think about it again. Okay, so about the select line, what we can do is we can simply tie it to decrement. So if the decrement is 1, I can take this input, and if decrement is 0, then I can load the initial value. But it won't work fine, because let's say on 1 second boundary I decremented it, but as soon as the decrement signal is low, it will write down the initial value again. So we decremented it from 60 to 59 for a cycle, but in the next cycle, since the decrement will be zero, initial value will be loaded again, that we don't want. So what we can do is we have to control when we want to write on this register. So we have to do two things. First is to select things, but also we have to control when we want to write on this register. We don't want to write on this register on every cycle. So if we don't want to write on a register on every cycle, that means that register needs a enable signal. So we have to have an enable. And if we do it correctly, what we can do is we only want to enable this register if there is a decrement signal or a load signal. So so as I am saying it, that we only want to enable it if there is a decrement signal or there is a load signal. So that or in the statement also gives you a hint that we can use an or gate. So if we do that, then if there is a load signal or a decrement signal, this enable will be asserted. And since so if the decrement, if this was asserted due to decrement, this side will be connected. If it was it was selected due to load signal, then decrement will be zero at the time, and this value will be selected. There is a chance to have a decrement and a load on the same clock cycle, so we haven't handled this case in this specific design. But what we can do is we can use an XOR gate as for that case, and in that case, if there is a load and decrement at the same time, we won't enable the circuit, so the value will remain whatever it is. But it depends how we want to actually what circuit we are using it in. Maybe we want to prioritize decrement over load. Maybe we want to prioritize load over decrement. If we want to prioritize load over decrement, then instead of decrement, we will want to connect load signal to the mux, and then if that is one, we'll write this side, and otherwise we'll write this. Okay, so now let's do another example. So by now, your brain muscles might have flexed a little. So let's do another example and flex them a little bit more. So we want to make a 4D FIFO. So what is a FIFO? FIFO takes so FIFO is a common term in computer science. We have push and pop signals. When there is a push signal, we want to store this data in this FIFO, and when there is a pop signal, we want to bring out the data that was stored first in the FIFO. FIFO stands for first in, first out. So whatever value was written first, it will be output first. So, so what we want is, for example, we want to store 100 in the FIFO. So I'll insert a push signal and push data 100 here. That will be stored in the FIFO. Then I want to store 500. I'll push again and give a value of 500. So FIFO will have two values, 100 and 500. So if I want to pop it, so the first value that was written was 100. So at data out, always it should be the value that was written first. So if I pop it, that means that I have read that value, and now I can read the next value. So if I assert pop signal, that means that that 100 is already read out. So in the next cycle, the value that should be output should be 500, and so on. So by 4D, we mean that we can at max store four values in the FIFO. So if there are four pushes and there is no pop, that means that we can't push anymore. And since this is a simple design, we don't handle that case, but we would say that whoever is pushing has to make sure that he doesn't push if the FIFO is full. So we assert FIFO full signal if we have four consecutive pushes without pop. But if there is a pop, then that means there are three values stored, then we can push again, and so on. If there is if the FIFO is empty, then it shouldn't be any pop on the FIFO because there is no data available. So if there is a FIFO empty asserted, which will be at the start, and whenever we have popped out all values, then then pop should not be asserted. So think about it. What could be the design options? Yeah, pause for a moment and think about it. Okay, so uh, again, when I think about it, we need at least four registers to store the values. There can be multiple design options, but one way to design is that I always push this way. So I connect data in with first register and the data out of first register to data in of second, and so on till the four registers are there. So whenever I push a data, that data will be written on this register. The data that was written in this register will be moved to the next and the next and next, and the data written in the last register will be lost. Since at the start we don't need any data, so what we initialize them with zeros, and this value can be overwritten. We don't care about it because there was no data in the FIFO. But if four pushes have been done, then first value will be here, second will be here, third will be here, fourth will be here. So to write it, right side is pretty simple. We just need to write everything whenever there is a push. So we can, do we need an enable signal here? Think about it. Yes, we do, because we only want to push when there is a push signal. So we can push, we can use push as an enable signal of this register. Okay, so this right side was simple. How can we read from it? So for example, if I've written three values, one is stored here, one is there, one is there. So the first value will be here. But if I had written only two values, that value would have been here. If I had only pushed one value, that would have been here. So that means I need to be able to read from here, 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 and here. So I have to read from four different locations. So that means I need to connect this data out with any one of them, depending on how many times I have pushed the data. So when we have multiple inputs and we want to connect it to one output, what do we use? That's right, we use a mux. So we use a mux that can select between four inputs. So that means it will be two select lines, because with 2 bits we can have values 0, 0, 0, 1, 1, 0, and 1, 1, that is 0, 1, 2, and 3. But how can we select this select line? How do we know that whether we want to read from here, here, or here, or here? It depends on how many times we have pushed it. And it also depends on whether we popped some data or not. For example, if I had pushed 4 times, then data will be here. So I should have 1, 0, 1, 2, 3. So I would want this to be at the output. But if there has been a pop in between, then that value will be here. So we want some kind of counter here that can count pushes as well as pops, but we want to increment on push and we want to decrement on pop. So that counter can also give us signals that if it is 4, then FIFO is full, and if it is 0, then FIFO is empty. So that's kind of the design, that RTL level design that we are looking into. So, but we haven't designed this counter yet. So rest of the logic is pretty much designed. This is a comparator. These are registers and muxes. So how about this counter? So so we want a counter. You have already made a counter, the decrementary example, in the decrementary example. So in this example, we don't want to load an initial value. We want to start at 0, and whenever there is an increment, we want to increment it, and whenever there is a decrement, we want to decrement it. Again, we need a register that holds the count value, and we want to decrement as well as increment it. So we need a decrementer as well as an incrementer. And since we want to store one of those values, so we also need a mux, just like in the previous example. And again, the select line can be increment, and we can have an enable that only if there is an increment or decrement, then we can enable this register. So if the increment is 1, so this value would be written. If decrement is 1, this value is written. If both are 0, then by default decremented value will be selected because its select line is 0, but it won't be written because if both inputs are 0, enable will be deserted. So now we have designed the counter as well. So again, what I want to show with these examples is that until we have this level of design diagram available, we don't write Verilog code. We have to reach state unless we have this design diagram. If we don't do that, we'll make mistakes and we'll be writing in a software style, and that doesn't work in hardware. So you have to come out of this mentality of writing software, because Verilog is a language, but it's a hardware description language. Whatever we write describes hardware. So I've seen codes where people have written spaghetti code that runs in simulation but doesn't run on FPGA because they haven't gone through the design process correctly. Okay, So, in addition to the components that we design, there also exists a library of components, common components that are used. We generally call them IP cores. For example, FIR filter, if we are using as we doing a signal processing example, FFT core, also for signal processing, error correction codes for if we are working on communication systems. Similarly, there are image processing libraries available as well. So there's a lot of components that are available in open source domain, as well as in form of IP cores that are ready to use, that are blocks that you only need to study the document, how they work, and then interface with those things. Okay, so I'll stop here, and in the next section I'll cover how to write Verilog code.